These are notes for section 1-3, midpoint and distance. Pause to write down your I can statement and review 2 key vocabulary words. Now that you're back, let's go to example 1. I'm going to ask you to first pause and write down our midpoint formula. And now that you're back, we're going to do an example together of how to use it. So we know that the midpoint is literally the middle point between two endpoints. And now this is going to tell us how to algebraically find it. So example 1a tells us that we want to find the midpoint between point C, which is located at -2, 5, and point D, which is located at 8, -12. The first thing we are always going to do is write down our formula because we do not want to mess anything up. So x1 plus x2 over 2, y1 plus y2 over 2. So we're adding up the x coordinates dividing by 2, adding up the y coordinates dividing by 2. The next thing I want to review is reminding us that a coordinate is x comma y, and let's label our x's and our y's. So x1 just means the first x coordinate, which here is -2, and that means that our second x coordinate is 8. y1 and y2 are similar in that way. Our first y coordinate is 5. Our second y coordinate is -12. Now we're ready to substitute that in and truly find our midpoint. So let's add up our x1 and our x2, which would be -2 plus 8 divided by 2. Our y1 and our y2 would be 5 plus a -12, or 5 minus 12 divided by 2. And now we're ready to simplify. -2 plus -8 is -6 over 2. 5 plus a -12, or 5 minus 12, is a -7 over 2. We can actually do this division now, and we find that our midpoint, our middle point, is located at when x is -3 and when y is -3.5. Since it's a midpoint, we do need both of these components. Both of those components, the x and the y coordinate. I want you to pause and try part B, and then I'm going to come back and delete this sticker so you can check your work. So pause, try it. All right, now that you're back, check it. Did you get it right? Email me if you don't know where you messed up. Example 3 is deriving the distance formula. So if you're in your workbook, it's going to give you a problem like what it says here, let's try it. But before we can even answer that, we need to understand what the distance formula is. So we're going to do this together, and I did not pre-draw this because I want to do it with you. We're going to draw a little x and y coordinate plane, so a y-axis and a little x-axis. It does not need to be perfect. We are not artists. And we're going to draw some segment PQ. So some starting point P, some ending point Q. We're going to draw that segment. What we are being tasked with right now is figuring out what is the distance between P to Q. And now we don't know what point P is at, just some x1, y1, because it's our first point. Q is at some x2, y2, because it's our second point that we don't know. And we're using our variables with little subscripts to represent them. How are we going to find the distance between these 2 points? We're going to use the Pythagorean theorem. And if you remember the Pythagorean theorem, it tells us that a squared, some leg A of a right triangle squared, plus some leg B of a right triangle squared equals c squared, which is the hypotenuse squared. And in this case, our hypotenuse is actually going to be that distance that we want, that d squared. But you might be thinking, hey, wait, what? We don't have a right triangle. We don't yet. We're going to draw one. So we're going to draw a bottom leg, and we're going to draw a side leg. And what we have created is a right triangle where the hypotenuse is the distance that we're looking for. Now, you might still be thinking, well, we don't know how long side leg A is, and we don't know how long side leg B is. We don't know them exactly, but we do know this x-coordinate and this x-coordinate. So we could say that A is going to be the difference between those x-coordinates, x2 minus x1, or x1 minus x2. We just know difference means subtraction. And we could say that side leg B is the difference between the y-coordinates, y2 minus y1. We can actually substitute those into our Pythagorean theorem, saying that leg A is the difference in our x's, and leg B is the difference in our y's. And it's really just the difference in the horizontal and vertical change of our segment. So now we have x2 minus x1 squared plus y2 minus y1 squared equals distance squared. The last thing we need to do is we don't want to know what distance squared is, we just want to know what the distance is. So how do we undo something squared? We take the square root of both sides. So if I take the square root of both sides, I'm left with the square root of x2 minus x1 squared plus y2 minus y1 squared equals my distance. And this is the distance formula. And now you can see how it was created using what we know about right triangles in the Pythagorean theorem. So if we want to try to actually answer this question, let's read it. Tavon claims that he wrote it and he subtracted x1 minus x2 and then y1 minus y2. Can this also be used? Yes. And that's because we know in the distance formula we are going to square whatever that distance is. So, I mean, that's the same as if we said 7 minus 2 equals 5 or 2 minus 7 equals negative 5. Since we're going to be squaring both of those, which just means to multiply it by itself, they'll both result in a positive number because 5 times 5 equals positive 25 and negative 5 times negative 5 also equals a positive 25. So in this case, since we're going to be multiplying that difference by itself, as in squaring it, yes, it truly doesn't matter as long as you are keeping the x values together and you are keeping the y values together using subtraction. It doesn't necessarily matter what order you subtract them in. Now let's actually use this distance formula. In example 4, it had a diagram in our textbook that for some reason is not in your workbook. I am not going to ask you guys to draw it, but during this video note, I just want you to make sure you're looking at this baseball diagram. And it says, how far does the shortstop, so let's find the shortstop, he's up here. How far does the shortstop need to throw the ball to reach the first baseman? Round your answer to the nearest tenth of a foot. And they have thrown our baseball grid on a coordinate grid. So we actually can find the location of the shortstop. So I'm going to zoom in so you can find the location of the shortstop. What is his coordinate location? Hopefully you said 5, x, 10, y. And our first baseman is located when x is 10 and y is 0. There is no vertical shift there, no vertical movement. And now we're actually going to just use this distance formula, noting that our x1s are, our x values are 5 and 10. Our y values are 10 and 0. I wrote the distance formula here for us because the first step of using any formula is writing it down. And now we can substitute it in. Let's do x2 minus x1, so that would be 10 minus 5 squared. And then y2 minus y1, which would be 0 minus 10 squared. Let's do those calculations. 10 minus 5 would leave me with 5 squared. 0 minus 10 would leave me with a negative 10 squared. Ooh, I want to change that color. I want this to be pretty, or kind of pretty. So now we have the square root of 5 squared plus negative 10 squared. 5 squared is 25. Negative 10 squared, here's that perfect example. A negative times a negative is a positive, so that's actually 25 plus 100, positive 100. If we add those together, we are now evaluating the square root of 125. Now, whatever calculator you're working with, whether it be something on a Chromebook, an iPhone, an online calculator, anything, when you get the square root of 125, you're going to get approximately 11.18. But I do not want you to close out of that calculator. Let's leave it up because we want to make sure we're answering the question. So the question tells us, how far does the shortstop need to throw the ball to reach the first baseman? And we have found that the distance between these 2 points is 11 point, approximately 18 units. But let's pay attention to something that's in this diagram that is easy for us to miss, but since we are math scholars, we're going to zoom in and we're going to see it. 1 unit is 9 feet. That's going to be really important for us. 1 unit is 9 feet. And we just calculated his distance in units. So we actually need to know if it's 11.18 units and there's 9 feet per unit, we need to multiply that by 9 in order to figure out how many feet it is. So I want you to actually go back into that calculator and pull up the 11.18 long decimal, multiply that by 9, and then we can round to the nearest tenth of a foot. So if you do that and you multiply that by 9, you should, and then you round, you should end up with about 100.6 feet. So that tip, anytime you're doing a calculation on top of a calculation, don't round until the very end. Don't cut anything off until the very end, because that could impact your answer. If we round too early, if we would have rounded too early and then we multiplied by 9, we might have gotten a different answer and we're not actually correct. So these were examples of how to use the midpoint and distance formula. These formulas will not change. You will use them for all of your practice, and go get started on that practice. Rewind and watch as needed.